For much of human history, the Andromeda Galaxy appeared as nothing more than a faint blur in the night sky. Many regarded it as a nebula, a mere cloud of gas within the bounds of our own Milky Way. Yet, some visionaries dared to speculate it might be an entire galaxy in its own right. When the truth finally emerged, it completely upended our understanding of the cosmos. Andromeda is far more than just another celestial speck. It stands as the largest galaxy in our local group, harboring 1 trillion stars and a wealth of untapped mysteries. It also represents our cosmic destiny, as Andromeda and the Milky Way are set on a slow-motion collision course that will, over billions of years, merge them into a completely new entity. What enigmatic secrets does this neighboring galaxy conceal? Could it host planets we have yet to uncover? And one day, might humanity, or something born of us, traverse the vast intergalactic expanse to reach it? Nebula or galaxy? That was the defining question of the 20th century. In the early 1900s, astronomers grappled with a mystery that would forever transform our grasp of the universe. Was the Andromeda Nebula simply another gas cloud inside the Milky Way? Or was it a galaxy similar to ours, unimaginably distant? At that time, the universe, as most people saw it, was much smaller. Scientists generally believed that the Milky Way encompassed everything, every star, every planet, and every cloud of gas. When telescopes captured faint glowing patches of light in the night sky, astronomers categorized them as nebulae, assuming they were regions of interstellar gas potentially birthing new stars. Andromeda stood out among these mysterious objects, a luminous spiral-shaped smear distinct from countless other nebulae charted in the sky. The argument over Andromeda's true nature grew more intense as the 20th century unfolded. Some astronomers proposed that it was an independent stellar system, an island universe in its own right. This was a revolutionary notion. If Andromeda was a galaxy, then the universe was vastly larger than anyone had imagined. It would mean that the Milky Way was not the entirety of the cosmos, but merely one of countless galaxies scattered across space. A key argument against Andromeda being a separate galaxy was the prevailing belief that the Milky Way was immense enough to contain everything. In 1917, astronomer Harlow Shapley estimated the Milky Way size at roughly 300,000 light-years in diameter, an immense figure for that era. If Andromeda lay beyond the Milky Way, it would have to be millions of light-years distant, a staggering concept for many to accept. Shapley and like-minded astronomers maintained that all known nebulae were within our galaxy and that hypothesizing the existence of other galaxies was unnecessary. Opposing this view was Heber Curtis, another prominent astronomer. Curtis highlighted observations suggesting Andromeda might lie far beyond the Milky Way. One major clue came from novae, exploding stars that flare brightly before fading. Curtis noted that novae in Andromeda appeared much dimmer than those within our galaxy. If they were indeed the same kind of event, the only logical explanation was that Andromeda lay far farther away than previously thought. Curtis also emphasized Andromeda's spiral structure, which resembled other enigmatic spiral nebulae observed in the sky. If these spirals were simply gas clouds inside the Milky Way, it was unclear why they displayed such distinctive, organized patterns. However, if they were independent galaxies, their spiral shapes made sense. They were sprawling collections of stars, much like our own Milky Way. This scientific conflict culminated in 1920 at a historic meeting later dubbed the Great Debate. Shapley and Curtis publicly presented their contrasting views at the Smithsonian Institution, each laying out evidence for and against the idea that Andromeda was a separate galaxy. Shapley defended the single-galaxy model, contending that the Milky Way was so vast that no other galaxies needed to be considered. Curtis, in contrast, argued that Andromeda and other spiral nebulae were independent star systems. The debate concluded without a decisive winner. Both men had presented compelling cases, and at the time, no conclusive evidence settled the dispute. Yet, the quest for an answer pressed on. Within a few short years, the mystery of Andromeda would finally be unraveled. In 1924, Edwin Hubble made a groundbreaking discovery using the 100-inch telescope at Mount Wilson Observatory in California. Central to Hubble's work was a type of star known as a Cepheid variable. These stars pulse in a predictable rhythm, growing brighter and dimmer over time. Earlier, astronomer Henrietta Swan-Leavitt had uncovered a crucial relationship. The longer a Cepheid's pulsation cycle, the more luminous it is. This meant that by measuring how quickly a Cepheid varied in brightness, astronomers could determine its true luminosity. Comparing this to how bright it appeared from Earth allowed them to calculate its distance. When Hubble calculated the distance to Andromeda, the result was astonishing. It was over 2 million light-years away. This placed Andromeda far beyond the boundaries of the Milky Way, conclusively proving that it was a separate galaxy. Hubble's discovery revolutionized astronomy overnight. The Milky Way was no longer the entirety of existence. It was merely one among countless galaxies, each teeming with billions of stars. The long-standing debate was finally resolved. The once theoretical idea of island universes had become reality. This revelation paved the way for even greater discoveries. As telescopes improved, astronomers uncovered ever more galaxies stretching across the cosmos, some even larger than the Milky Way. Realizing that our galaxy was just one among many sparked new questions about the universe's size, structure, and origins. The field of cosmology expanded rapidly, moving from a narrow focus on the Milky Way to an exploration of the universe in its entirety. Even after Edwin Hubble's discoveries transformed astronomy, doubts and unresolved questions lingered. Science rarely progresses in a straight line, and confirmation of Andromeda's status as a galaxy did not eliminate all uncertainties. Some astronomers hesitated to fully accept the new model of the universe, and certain early observations seemed to conflict with the concept of multiple galaxies. One of the major lingering concerns centered on the brightness of galaxies. If these galaxies truly lay millions of light-years away, their intrinsic brightness had to be far greater than anyone had previously imagined. Some scientists struggled with the idea that individual galaxies could emit so much light across such immense distances. It posed a significant challenge to explain how these colossal structures produced such brilliance, especially when astronomers still lacked a complete understanding of how stars generated energy. At the time, theories about stellar energy production were still unsettled. The now accepted idea that stars sustained themselves through nuclear fusion had not yet been fully established. In the early 20th century, many scientists believed stars shone due to gravitational contraction, slowly compressing under their own gravity to release heat. However, this mechanism could not account for stars shining steadily for billions of years. If galaxies, as Hubble's research indicated, contained billions of stars, a new explanation was needed to justify the enormous amounts of light emitted. This puzzle remained unresolved until the mid-20th century when researchers confirmed that stars are powered by nuclear fusion, transforming hydrogen into helium and releasing tremendous amounts of energy in the process. Astronomers also faced questions about how galaxies were distributed across the cosmos. If the universe contained countless galaxies, why did they appear concentrated in certain regions while other areas seemed nearly void? Early sky surveys revealed clustering patterns that were initially puzzling. These observations indicated that galaxies were not scattered randomly, but instead seemed to gather in groups and clusters. Some astronomers wondered whether these patterns were artifacts caused by limitations of early telescopes, while others suspected they reflected an intrinsic characteristic of the universe. If galaxies tended to form groups, what force was binding them together? Gravity seemed the obvious answer, yet scientists lacked the tools necessary to thoroughly study the large-scale motions of galaxies at that time. Further doubts arose from early attempts to measure the motions of galaxies. Although Hubble had shown that galaxies were generally receding from us, some astronomers observed peculiar exceptions. A few galaxies exhibited very little redshift, implying they were not moving away as rapidly as others. More intriguingly, Andromeda itself appeared to be moving toward the Milky Way rather than away from it. If the universe was expanding, why was this enormous galaxy on a direct course toward our own? Scientists later realized that while the universe's overall expansion dominated on large scales, it did not prevent nearby galaxies from having their own motions influenced by gravity. Andromeda and the Milky Way were close enough that their mutual gravitational attraction overpowered cosmic expansion, pulling them toward one another. Although Hubble had firmly established Andromeda's vast distance, questions remained about many other spiral structures catalogued in the sky. Were all of them as distant as Andromeda, or did some reside within the Milky Way? Astronomers had to painstakingly study each object to determine its true identity. In certain cases, what seemed to be a spiral nebula was later discovered to be something entirely different, like a planetary nebula or a supernova remnant within our galaxy. Distinguishing between galaxies and other celestial phenomena was not always straightforward. If galaxies were indeed immense star systems, how had their stars formed? Did all galaxies generate stars at the same rate? Early observations revealed that some galaxies appeared more active than others, but the reasons were not fully understood. Some contained brightly glowing regions suggesting vigorous star formation, while others seemed comparatively quiescent. Astronomers required more detailed observations to uncover what was driving these variations. If galaxies were independent systems, had they always existed in their present forms? Did they evolve over billions of years, or were they unchanging structures? Light from distant galaxies took millions, even billions, of years to reach Earth, But telescopes at the time were not yet powerful enough to peer far enough back in time to witness the universe's earliest galaxies. Scientists could only study the galaxies accessible to them and infer their histories based on available evidence. Despite lingering uncertainties, the idea that Andromeda was a separate galaxy gained widespread acceptance. The weight of evidence was simply too compelling to dismiss. Yet, every answer uncovered fresh questions, demonstrating that the exploration of galaxies was only just beginning. As astronomers moved beyond questioning whether Andromeda was a galaxy, they turned their focus to unraveling its composition and intricate structure. Also known as Messier 31 or M31, Andromeda gradually became one of the most extensively studied galaxies in the cosmos. What they discovered was a sprawling system teeming with billions of stars, swirling clouds of gas, enigmatic halos of dark matter, and a rich history of galactic mergers that shaped it over billions of years. Much like the Milky Way, Andromeda hosts stars of every age, from young, hot blue giants to ancient red dwarfs that have burned for billions of years. In the bright core of the galaxy, older red stars dominate, hinting at a long evolutionary past. These stars formed early, consuming much of the available gas. Yet in Andromeda's majestic spiral arms, dense clouds of gas and dust still linger, nurturing the birth of young stars. These regions glow with the light of hot blue stars formed relatively recently. In cosmic terms, a galaxy composed solely of ancient stars would indicate that it had long ceased forming new ones, while a galaxy filled with youthful stars would suggest it remained in the early stages of development. Andromeda, however, showcases a mixture of both, evidence that it has experienced cycles of star formation. At times, it has produced bursts of new stars, while at others, it has remained relatively quiet. These cycles are driven by the motion and interactions of gas, which provides the raw material for star creation. Andromeda's vast gas and dust reservoirs offer valuable clues about its ongoing evolution. Hydrogen, the universe's most abundant element, makes up much of this gas within the galaxy. Large hydrogen clouds drift between stars, occasionally condensing into denser regions where gravity draws the material together. If enough gas accumulates, rising pressure and temperature can ignite nuclear fusion, giving birth to a new star. In some cases, entire star clusters emerge from a single massive gas cloud. Interestingly, some of the gas does not align with the galaxy's general motion, hinting that Andromeda has absorbed smaller galaxies over time. When a dwarf galaxy ventures too close, Andromeda's gravity captures it, stripping away its stars and gas and incorporating them into its own structure. These galactic mergers have left behind faint stellar streams and disrupted gas patterns, subtle traces of ancient collisions that have sculpted the galaxy's current form. By analyzing the distribution of these isotopes, astronomers can determine which types of stars played a dominant role in shaping Andromeda's chemical composition. The patterns they have observed suggest that Andromeda experienced a different rate of star formation and possibly different kinds of stellar explosions compared to the Milky Way. When a galaxy merges with another, it not only absorbs stars but also acquires any unusual chemical signatures carried by the incoming system. Some of Andromeda's outer regions display signs of elements that do not match the typical composition of its main disk. These could be remnants of long-lost galaxies that were absorbed by Andromeda, leaving behind traces of their unique chemical identities. The core of the galaxy contains a higher concentration of iron and other heavy elements compared to the surrounding areas. This suggests that Andromeda's core may have undergone intense periods of star formation and supernova activity in the past. Some of these elements could have been created in short-lived massive stars that exploded violently, enriching the surrounding space with heavier materials. This process mirrors what astronomers have observed in other galaxies with active star-forming regions. Some studies have suggested that Andromeda has a slightly lower abundance of certain elements, such as magnesium, compared to what is typically expected for a galaxy of its size and age. This might indicate that Andromeda's chemical evolution was influenced by external factors, such as variations in its early environment or past interactions with other galaxies that altered its star formation history. Throughout the galaxy, dust grains composed of tiny solid particles of carbon, silicon, and other elements are scattered. These dust particles play a crucial role in the formation of new stars and planets by providing the raw materials needed to build planetary systems. The chemical composition of this dust varies across Andromeda, with some regions containing more carbon-rich grains, while others are dominated by silicate materials similar to the rocky substances found on Earth. One of the primary tools scientists use to analyze Andromeda's chemical fingerprints is spectroscopy. By studying the light emitted or absorbed by different elements, astronomers can determine the precise composition of the galaxy. This technique has revealed the presence of molecules such as carbon monoxide, which is often found in dense clouds when new stars are forming. The detection of these molecules helps researchers understand how Andromeda continues to evolve and produce new generations of stars. As the galaxy continues to form stars, its overall metallicity, the abundance of elements heavier than helium, will gradually increase. However, as its supply of raw gas is slowly depleted, the rate of star formation will decline. Eventually, Andromeda will become a galaxy dominated by older stars, with fewer new ones being born. When it ultimately merges with the Milky Way in approximately 4 billion years, the resulting combined galaxy will carry the chemical fingerprints of both systems, blending their histories into a new cosmic identity. Andromeda is home to an immense variety of stars, many of which follow predictable life cycles and are similar to those seen in other galaxies. However, scattered among these common stars are rare and unusual types. Some are remnants of violent cosmic events, while others are still forming in ways that challenge current models of stellar birth. One of the most intriguing groups of ray stars in Andromeda is the population of luminous blue variables. These massive, unstable stars are prone to sudden changes in brightness. They exist in a delicate balance between gravity and radiation pressure, with their outer layers frequently being blown away by strong stellar winds. One of the best-known examples in Andromeda is AE Andromedae, which has been observed fluctuating in brightness over time. These stars are believed to be in a short-lived phase of evolution before they explode as supernovae, making them key targets for understanding the final stages of massive stars. Scattered throughout Andromeda's spiral arms are a number of Wolf-Rayet stars, a rare and extreme class of hot, massive stars nearing the end of their lives. These stars have already lost most of their outer hydrogen layers, exposing the deeper, hotter regions where heavier elements are being formed. As a result, Wolf-Rayet stars emit powerful stellar winds and shine with an intense blue-white light. Their presence indicates regions of recent star formation, as they live only for a few million years before collapsing in dramatic supernova explosions. Andromeda also hosts hypervelocity stars, stars moving at extraordinary speeds that should not be possible under normal conditions. Some of these stars may have been ejected from binary systems when their companion exploded as a supernova. Others might have been flung outward after a close encounter with Andromeda's supermassive black hole. These hypervelocity stars travel so quickly that some may eventually escape the galaxy entirely, carrying with them clues about the extreme gravitational forces at play within Andromeda. In the outer reaches of the galaxy, a different kind of rare star appears, carbon stars. These stars have an unusual abundance of carbon in their atmospheres, giving them a distinctive reddish glow. Carbon stars are thought to form when convection within the star dredges up carbon from deeper layers, enriching the outer atmosphere. This process alters the way the star emits light, making it appear redder than normal. Andromeda's carbon stars are particularly interesting because they reveal how chemical elements are recycled in galaxies over time. These stars shed carbon-rich material into space, helping to enrich the interstellar medium with the raw materials needed for future star and planet formation. Deep in Andromeda's central bulge, astronomers have identified an unusual population of extremely metal-poor stars, stars that formed in the early history of the galaxy when heavier elements were still scarce. These stars are relics from a time when the universe was much younger, and their compositions offer a glimpse into the conditions that existed billions of years ago. Because they contain so few heavy elements, they are believed to be some of the oldest stars in Andromeda, possibly dating back to the period when the galaxy was just beginning to take shape. Yellow supergiants are another rare category of stars found in Andromeda. These stars are caught in a brief transition phase between being red supergiants and blue supergiants, making them difficult to observe. Yellow supergiants are rare because this evolutionary stage lasts only a few thousand years, a mere blink of an eye in cosmic terms. Their presence in Andromeda provides valuable data about the life cycles of massive stars, helping astronomers refine their models of how such stars change over time. Perhaps one of the most unusual types of stars in Andromeda is the magnetar, a neutron star with an incredibly powerful magnetic field. These remnants of collapsed massive stars emit bursts of high-energy radiation and possess magnetic fields trillions of times stronger than Earth's. The detection of magnetars in Andromeda suggests that the galaxy has experienced a significant number of supernova explosions, each leaving behind one of these highly magnetized remnants. The study of these exotic objects helps scientists understand extreme physics in ways that cannot be replicated in laboratories on Earth. Variable white dwarfs are another fascinating stellar remnant in Andromeda. These tiny but dense cores of dead stars occasionally display unexpected variations in brightness, caused by pulsations or interactions with surrounding material. Unlike more common white dwarfs, these ray versions may be part of binary systems where they slowly pull material from a companion star. In some cases, this process can trigger a sudden thermonuclear explosion known as a nova, temporarily making the white dwarf thousands of times brighter before it fades back into obscurity. Each new observation of these phenomena adds to the growing understanding of how stars evolve, how galaxies change over time, and how different cosmic environments influence the life cycles of stars. These hidden luminaries, often overlooked in broader discussions of galaxies, provide essential clues about Andromeda's past and its future. They demonstrate that even within a well-studied galaxy, there are still mysteries waiting to be uncovered. Andromeda is not merely a collection of isolated stars but a vast cosmic landscape where stars gather in clusters, forming communities that evolve together. Some of these clusters are dense and ancient, while others are loosely bound and relatively young. One of the most striking types of clusters found in Andromeda is its population of globular clusters. These dense spherical groupings of stars are among the oldest structures in any galaxy, often containing stars that formed early in cosmic history. Andromeda has far more globular clusters than the Milky Way, with estimates suggesting over 500 of them orbiting the galaxy. Some of these clusters, however, appear different from those typically seen in other galaxies. A few contain stars that are significantly younger than expected, raising intriguing questions about how they formed. Other clusters seem to exhibit unusual motions, suggesting they may not have originally belonged to Andromeda but were captured from smaller galaxies during past collisions. Astronomers have also identified a surprising number of extended clusters in Andromeda, groups of stars that are not as densely packed as traditional globular clusters, but still remain gravitationally bound. These extended clusters are unusual because they blur the line between star clusters and small galaxies. Unlike typical globular clusters, which are tightly bound and spherical, extended clusters have more spread-out structures and lower overall densities. Some scientists believe these objects could represent a transitional phase between clusters and dwarf galaxies, offering a rare glimpse into how galactic structures evolve over time. A particularly mysterious type of star cluster in Andromeda is the so-called faint fuzzy cluster. These clusters, first identified in Andromeda's outer regions, appear distinct from both globular clusters and open clusters. They contain old stars similar to globular clusters but are more loosely structured, making them less likely to survive for billions of years without being disrupted by gravitational forces. Some theories suggest they may have originated in a long-ago merger between Andromeda and a smaller galaxy, leaving behind remnants that have slowly dispersed over time. Andromeda also hosts an unexpected number of young, massive clusters containing bright, hot stars that are only a few million years old. The presence of these young clusters is surprising because many are found in regions where star formation was thought to have largely ceased. Some of these clusters are located far from Andromeda's main star-forming regions, leading to speculation that they may have been formed by tidal interactions or triggered by past collisions with satellite galaxies. There are also star clusters in Andromeda that do not match the chemical composition of the rest of the galaxy. Some of these contain stars with unusual metal ratios. A few clusters even appear to have compositions more similar to those found in dwarf galaxies rather than in a large spiral galaxy like Andromeda. This suggests that Andromeda has been absorbing smaller galaxies over time, with their star clusters becoming part of its stellar population. Studying these clusters provides evidence of Andromeda's history of mergers and acquisitions, allowing astronomers to reconstruct past events that shaped the galaxy into what it is today. The distribution of star clusters within Andromeda also raises intriguing questions. Some clusters are found in regions where they should have long since been disrupted by gravitational forces, while others form patterns that suggest they may have originated from larger structures. Certain clusters even appear to be arranged in streams or arcs, possibly remnants of past mergers. These patterns imply that Andromeda's halo is still being shaped by ongoing interactions with smaller galaxies. Some of Andromeda's overlooked clusters are even more difficult to classify. A handful of clusters contain extremely massive stars that should not have survived for billions of years, while others harbor an unusual mix of stars, with some appearing much younger than expected. These anomalies have led to speculation that some clusters might be temporary, held together only loosely by gravity and destined to eventually dissolve into Andromeda's general stellar population. Advanced telescopes have revealed additional star clusters hidden in the dense regions near Andromeda's core, where they were previously obscured by dust and bright stellar light. These central clusters may hold valuable clues about the supermassive black hole at Andromeda's heart, possibly interacting with its powerful gravitational forces. Other discoveries include star clusters at extreme distances from the galaxy, raising questions about how far Andromeda's influence extends into intergalactic space. At the heart of Andromeda lies one of its most powerful features, a supermassive black hole. This immense object, hidden deep within the galaxy's core, influences everything around it, shaping the motion of stars, bending light, and consuming matter that strays too close. Scientists have long suspected that most large galaxies harbor such black holes at their centers. Observations reveal that Andromeda's supermassive black hole, called M31*, is about 140 million times the mass of the Sun, making it significantly more massive than the Milky Way's central black hole, Sagittarius A star. The presence of such a massive object at Andromeda's core raises important questions about how it formed and grew to its current size. Some theories suggest that as Andromeda absorbed smaller galaxies over billions of years, each of these galaxies brought its own black hole. Over time, these black holes merged, creating a single larger one at the galaxy's center. Surrounding M31*, Andromeda's supermassive black hole, is a dense, compact cluster of stars, an unusual feature that sets it apart from other galactic centers. These stars move at incredible speeds, pulled by the immense gravitational force of the black hole. Observing their rapid orbits helped astronomers confirm the black hole's existence, as only such an extreme concentration of mass could account for the star's behavior. Unlike some other galaxies, Andromeda's black hole does not currently appear to be consuming large amounts of matter. In many galaxies, black holes form what is known as an active galactic nucleus, where gas and dust swirl around them, heating up and emitting powerful radiation. Andromeda's black hole, however, is relatively quiet, releasing only small amounts of X-ray and radio waves. Scientists believe this may be a temporary phase. It is possible that in the past, the black hole was more active, drawing in material and releasing energy that could have shaped Andromeda's core. Future encounters with gas clouds or entire star systems could reignite its activity, turning it once again into a powerful and energetic feature of the galaxy. Beyond the central black hole, Andromeda may also contain smaller intermediate-mass black holes scattered throughout its structure. These black holes, ranging from hundreds to thousands of times the mass of the Sun, are thought to form from collapsing massive stars or from the merger of smaller black holes. While supermassive black holes dominate galactic centers, intermediate-mass black holes remain difficult to detect and are among the most elusive objects in astronomy. Some of these smaller black holes may reside in the dense star clusters orbiting Andromeda. There is growing evidence that certain globular clusters may harbor black holes at their centers, subtly influencing the movement of surrounding stars. If confirmed, these intermediate black holes could help explain how supermassive black holes grow over cosmic time. Some scientists have even suggested that Andromeda's clusters may contain multiple black holes, creating complex gravitational interactions that could eventually result in the formation of larger black holes through repeated mergers. These black holes do not always remain in fixed locations. Some wander through the galaxy, drifting as a result of past galactic collisions or ejected from their original positions by powerful gravitational forces. A few may be remnants of smaller galaxies that Andromeda consumed in the past. Though black holes are extremely difficult to detect unless they interact with nearby matter, their gravitational influence can sometimes be observed when they pass in front of distant stars, momentarily bending and magnifying their light in a process known as gravitational lensing. These unseen objects exert powerful gravitational forces that can affect star formation, disrupt planetary systems, and even alter the paths of entire star clusters. If Andromeda harbors a large number of these hidden black holes, they could play a significant role in shaping the galaxy's future evolution. Gravitational wave detectors, which sense ripples in spacetime caused by merging black holes, may also help identify these elusive objects within Andromeda. As technology improves, astronomers hope to explore these enigmatic features in greater detail, uncovering more about their origins and their impact on the galaxy. Yet black holes are only part of the invisible framework holding Andromeda together. Without dark matter, Andromeda, along with the Milky Way and countless other galaxies, would not exist in its current form. One of the first clues to dark matter's presence in Andromeda came from observing how the galaxy rotates. If Andromeda consisted only of the stars, gas, and dust visible to astronomers, then the outer regions of the galaxy should be moving much more slowly than the inner parts. However, the observed rotational speeds suggest otherwise. The simplest explanation is that Andromeda is surrounded by an enormous halo of unseen material, dark matter, stretching far beyond the visible edges of the galaxy and outweighing all its stars and gas combined. The sheer amount of mass required to explain Andromeda's motion suggests that dark matter makes up most of the galaxy's total mass. Without it, the gravity of the stars, planets, and gas clouds alone would not be enough to hold the galaxy together. Moreover, the distribution of dark matter in Andromeda is not uniform. Some regions appear to have higher concentrations than others. Scientists have mapped dark matter using gravitational lensing. By studying how light from distant objects bends as it passes through different parts of Andromeda's halo, astronomers can piece together an image of this invisible material. These studies suggest that dark matter is not completely smooth, but instead is a clumpy structure, possibly shaped by interactions with smaller satellite galaxies or by internal gravitational forces within Andromeda itself. The presence of dark matter also affects how Andromeda interacts with its neighbors. Andromeda is part of the Local Group, a collection of galaxies that includes the Milky Way and dozens of smaller galaxies. The gravitational pull of dark matter in Andromeda's halo extends far beyond its visible borders, influencing the motion of nearby galaxies. Some of these, like the dwarf satellite galaxies orbiting Andromeda, may be held in place by dark matter's gravity, preventing them from drifting into deeper space. Others may be slowly falling toward Andromeda, drawn in by its unseen mass. One of the larger mysteries surrounding dark matter in Andromeda is what will happen when the galaxy collides with the Milky Way in a few billion years. The visible stars and gas clouds of both galaxies will interact dramatically, forming new star clusters and altering their structures. But dark matter, which does not interact in the same way, will behave differently. Rather than colliding directly, the dark matter halos of the two galaxies will pass through one another, their immense gravity reshaping the structure of the resulting merged galaxy. If dark matter is made of weakly interacting particles, as many theories propose, its distribution after the collision could offer valuable clues about its properties. On the other hand, if dark matter interacts with itself to some degree, there may be unexpected patterns in how the galaxies merge. Did dark matter form at the same time as the rest of the galaxy? Or was it already present in the early universe, shaping the first galaxies long before stars began to shine? Some theories suggest that dark matter particles were created in the moments after the Big Bang, spreading throughout the universe and acting as the foundation upon which galaxies like Andromeda later formed. Others propose that dark matter could be linked to forces or particles not yet discovered. Scientists hope that by mapping dark matter in greater detail and observing its effects on Andromeda's stars, they may one day unlock the mystery of this invisible but essential component of the universe. Mapping the giant innovations in galactic cartography has unveiled both the scale and complexity of Andromeda. One of the biggest challenges in mapping this galaxy is its sheer size. Even though it is the closest major galaxy to the Milky Way, Andromeda's sprawling structure does not fit neatly into the field of view of most telescopes. Observing the galaxy in its entirety requires assembling countless smaller images, a meticulous process that takes years of effort. The Hubble Space Telescope produced one of the most detailed views of Andromeda by stitching together thousands of separate exposures. This mosaic revealed millions of stars across a vast stretch of the galaxy, providing an unprecedented panoramic glimpse into its stellar population. Yet, mapping Andromeda involves far more than just capturing images. Scientists must also measure distances, analyze motions, and determine the composition of its various regions. One key method used in galactic cartography is spectroscopy. This technique allows astronomers to determine the chemical makeup, temperature, and movement of stars and gas clouds. It enables researchers to map not only where stars are located but also how they interact with one another and how the galaxy has evolved over time. Motion mapping is another crucial tool. Andromeda is not a static object. It rotates, shifts, and continually pulls in smaller galaxies. To track these motions, astronomers utilize Doppler shifts, measuring how the wavelength of light changes as an object moves toward or away from us. By analyzing these shifts across different parts of Andromeda, scientists can create detailed rotational maps, showing how various regions spin at different speeds. However, interstellar dust poses a significant challenge. Dust scatters and absorbs light, making it difficult to observe some parts of the galaxy. Certain regions are almost completely hidden in visible wavelengths. To overcome this, astronomers employ infrared telescopes that can peer through dust clouds and reveal structures that visible light obscures. The Spitzer Space Telescope provided a new perspective on Andromeda by mapping its dust-rich regions, offering insights into where new stars are forming. Andromeda also contains vast amounts of hydrogen gas, which emits a distinct wavelength of radio waves detectable even in regions shrouded by dust. By mapping these emissions, scientists can construct a blueprint of Andromeda's gas distribution, showing where stars are likely to form and how the galaxy replenishes its stellar population. Advancements in computational modeling have revolutionized galactic mapping. Instead of relying solely on direct observations, astronomers now use simulations to recreate Andromeda's structure and evolution. These models incorporate factors such as star distribution, dark matter influences, and gravitational interactions with neighboring galaxies. By comparing simulated versions of Andromeda with actual observations, scientists can refine their understanding of how the galaxy formed and how it continues to evolve. Andromeda's satellite galaxies are also carefully charted. Some, like M32 and M110, are easily visible, while others remain faint and difficult to detect. Large-scale surveys have revealed an entire system of dwarf galaxies orbiting Andromeda. Tracking these satellites helps astronomers understand Andromeda's gravitational influence and offers insights into how large galaxies grow by absorbing smaller ones. One of the most ambitious mapping efforts centers on Andromeda's impending collision with the Milky Way. Scientists are using detailed observations and motion studies to predict precisely how the two galaxies will interact when they begin merging in about 4.5 billion years. By charting the movement of stars and gas within Andromeda, astronomers have created computer models simulating how the galaxies will combine, ultimately forming a new, larger galaxy in the distant future. Despite these efforts, many mysteries remain. Some regions of the galaxy are still poorly understood, and new technologies will be required to uncover their secrets. Future space observatories, like the upcoming Nancy Grace Roman Space Telescope, are expected to provide even more detailed maps of Andromeda. These next-generation tools will allow astronomers to study individual stars, identify hidden structures, and refine models of the galaxy's formation and evolution. Surrounding Andromeda are dozens of smaller galaxies, its cosmic companions, each one orbiting and interacting with the giant spiral in complex ways. These satellites range in size and shape, from compact elliptical dwarfs to irregular systems that appear to be in the process of being torn apart. Some are easily visible even with amateur telescopes. M32 and M110 are the two most prominent, located relatively close to Andromeda's bright central region. M32 is a compact elliptical galaxy with a dense concentration of stars, while M110 is slightly larger and more diffuse, showing evidence of past interactions with its massive host. Both of these companions are thought to be remnants of larger galaxies that Andromeda stripped of gas and outer layers long ago. Beyond these bright satellites, many fainter dwarf galaxies orbit Andromeda at greater distances. Some, like NGC 147 and NGC 185, resemble small elliptical galaxies with minimal star formation and older stellar populations. Others, such as IC10, are still actively forming stars, indicating that they have managed to retain their gas despite Andromeda's gravitational pull. Early models suggested these satellite galaxies should be scattered randomly, orbiting in different directions with no clear pattern. However, recent observations revealed something unexpected. Many of Andromeda's satellites appear to be arranged in a vast, thin plane rather than dispersed evenly in space. This discovery challenges existing theories of galaxy formation, hinting that these satellites may have formed from a single event rather than being captured independently over billions of years. Some astronomers propose that Andromeda's satellite system is part of a much larger cosmic structure, possibly connected to the Milky Way's own group of dwarf galaxies. The idea is that these small galaxies may not be isolated objects, but instead components of vast cosmic filaments, long strands of dark matter and gas that stretch between galaxy clusters. Several of these satellites are in the process of being consumed. Their stars and gas are stretched into long streams as they spiral inward toward Andromeda. Observations have revealed enormous arcs of stars and gas extending outward from the galaxy, believed to be remnants of past mergers. These stellar streams provide direct evidence that Andromeda has grown through the absorption of smaller galaxies, a process that is still ongoing. One of the clearest examples of this galactic cannibalism is the discovery of the giant stellar stream, a massive ribbon of stars stretching over 100,000 light-years across space. This stream is thought to be the remains of a dwarf galaxy that ventured too close to Andromeda and was gradually torn apart by tidal forces, leaving behind a sprawling trail of stars across the sky. The stars now being absorbed into Andromeda's halo once belonged to a smaller, separate galactic system. As they merge, they become indistinguishable from Andromeda's broader stellar population. But these interactions are not entirely one-way. Though Andromeda is the more massive player, its satellite galaxies also exert influence. Their gravitational pull, though subtle, can distort the outer shape of Andromeda, gently warping its disk. Over immense spans of time, such gravitational interactions could reshape Andromeda's structure, playing a role in its future evolution. Because these dwarf galaxies are both small and faint, their motions are highly sensitive to the surrounding dark matter. By observing their orbits, astronomers can gather insights into how dark matter is distributed around Andromeda. Some of these satellite galaxies seem to be composed almost entirely of dark matter. These so-called dark galaxies contain very few stars and lack much visible gas, yet their mass is evident through their gravitational effects. Their presence raises intriguing questions about galaxy formation and whether a multitude of such invisible systems might exist across the cosmos. A portion of these satellites will eventually be drawn into Andromeda, their stars becoming part of the larger galactic population. Others may be cast off into deep space as a result of gravitational encounters. As Andromeda itself drifts closer to the Milky Way, its satellite systems may also be disrupted, possibly leading to new mergers and collisions in the far future. Supernova remnants are echoes of dramatic stellar transformations. A supernova marks the end of a massive star's life, triggered either by the rapid collapse of a giant star or the catastrophic explosion of a white dwarf in a binary system. These events release tremendous energy, scattering heavy elements into space and sending shock waves rippling through the surrounding regions. In Andromeda, such supernovae have been crucial in enriching the galaxy with new elements, shaping clouds of gas and dust, and even initiating the birth of new stars. One of the most studied remnants in Andromeda is that of SN 1885A, a supernova observed from Earth in 1885. Unlike many others that fade into obscurity, this remnant remains an object of scientific interest. It was a Type Ia supernova, the result of a white dwarf accumulating too much mass in a binary system and undergoing a runaway thermonuclear reaction. What makes SN 1885A particularly fascinating is its proximity to Andromeda's galactic center. The explosion left behind distinct traces of iron and other heavy elements. Even today, astronomers can detect its faint signature when observing that region. This event helped establish that Andromeda, like the Milky Way, is capable of hosting such monumental cosmic explosions. Beyond isolated examples, Andromeda is home to a wide network of supernova remnants, many of which are only visible through X-ray or radio telescopes. These remnants often appear as glowing shells of gas, still energized by the shock waves of the initial explosion. Some are relatively young, just a few thousand years old, and continue to visibly reshape their surroundings. Others are far older, their original forms now diffused into the interstellar medium as their energy gradually disperses. The shock waves from these blasts agitate nearby gas clouds, compressing them and sometimes triggering the formation of new stars. Without these explosions, which recycle elements and distribute them throughout the galaxy, Andromeda would look very different. The heavy elements essential for rocky planets, life, and complex chemistry owe their origin to these powerful events. By charting these remnants, astronomers can map out where earlier generations of massive stars once lived. Many are located in the spiral arms, regions with ongoing star formation spanning millions of years. Yet others are found in surprising places, revealing past periods of activity that aren't immediately visible through other observational methods. A few of Andromeda's remnants stand out due to their exceptional energy output. Often linked with fast-spinning neutron stars or pulsars, these remnants hint that some supernovae left behind more than just expanding clouds. They created dense stellar cores that continue to emit radiation long after the initial blast. These pulsars serve as cosmic lighthouses, enabling scientists to investigate the physics of extreme matter and the forces shaping Andromeda's development. The impact of these explosions reaches far beyond the visible remnants. Their shock waves blend with interstellar clouds, altering their chemical makeup. They also accelerate cosmic rays, high-energy particles that travel through space at nearly light speed. These rays help heat and ionize gas within Andromeda, influencing the conditions necessary for star formation. When supernova remnants appear in unexpected locations or show unusual traits, it may point to ancient mergers that added foreign material to the galaxy. Some of the oldest remnants may not have originated in Andromeda itself, but were carried in by smaller galaxies that were absorbed over time. Then there are variable stars, pulsing lights in the galaxy's rhythm. These stars are critical tools for astronomers, acting like cosmic yardsticks that help measure distances, monitor stellar life cycles, and unravel the structure of galaxies. Unlike ordinary stars, variable stars don't shine steadily. Their brightness fluctuates, sometimes in predictable intervals, sometimes erratically. Thousands of such stars have been catalogued in Andromeda, each one revealing different facets of the galaxy's complexity. Among them, Cepheid variables are particularly renowned. Cepheids are still among the most accurate tools for measuring cosmic distances, enabling astronomers to gauge the scale of Andromeda. But they are not alone. Ir Lyrae stars, another type of variable star, follow a similar rhythm, but are generally older and less massive. These Ir Lyrae stars are mostly found in Andromeda's halo and globular clusters, where ancient stellar populations reside. Their regular pulses allow astronomers to trace the oldest structures in the galaxy, mapping regions that have remained unchanged for billions of years. While Cepheids help determine distance, our Lyrae stars reveal the movement of ancient stars and evidence of long-past galactic interactions. The Andromeda Galaxy, with its staggering population of billions of stars, offers a vast and compelling frontier in the search for planets beyond our own. Within the Milky Way, astronomers have relied on several proven methods to detect exoplanets. Among the most successful is the transit method, which identifies slight decreases in a star's brightness as a planet crosses in front of it. Another key technique is the radial velocity method, which measures the subtle wobble in a star's motion caused by the gravitational pull of an orbiting planet. While these techniques work effectively for relatively nearby stars within our own galaxy, their effectiveness diminishes significantly when applied to much more distant galaxies. The immense distance to Andromeda makes it nearly impossible to observe its individual stars or planetary transits directly using current technology. Nonetheless, astronomers are innovating new strategies to overcome these limitations and expand the search to other galaxies. One particularly promising approach is gravitational microlensing. This method takes advantage of the way massive objects, like stars or planets, can bend and magnify the light from a more distant background star as they pass in front of it. If a planet is orbiting the intervening star, its gravitational field can cause a secondary brightening, hinting at its presence. Unlike the transit and radial velocity techniques, microlensing does not require direct imaging of the planet or even the ability to distinguish individual stars in another galaxy. In fact, in 2020, scientists reported a potential detection of an extragalactic planet in the Whirlpool Galaxy, inferred from subtle distortions in X-ray light emitted by a binary system. Though unconfirmed, this observation suggests that microlensing may become a critical tool in detecting planets far beyond the Milky Way. Applying this method to Andromeda is a natural next step. The galaxy's dense core, teeming with overlapping stars, provides ideal conditions for microlensing events to occur. With consistent long-term observation, astronomers might be able to detect brief, telltale brightening events that signal the presence of planets orbiting distant stars. Still, even if such planets are detected, verifying their properties would be extremely difficult. In our own galaxy, follow-up studies can provide insight into a planet's size, composition, and atmosphere. But in a galaxy as far away as Andromeda, scientists must rely on indirect evidence alone. Determining whether a planet is rocky, gaseous, or habitable lies beyond the reach of current instruments. Only future space telescopes, with far more sensitive capabilities, might eventually shed light on these distant worlds. Within the Milky Way, astronomers often focus on the habitable zone, the region around a star where conditions might support liquid water. Many discovered exoplanets lie within these zones, raising hopes about the potential for life. But extending this framework to Andromeda is far more complex. Even if a planet were found orbiting within a theoretically habitable zone, confirming the presence of water, an atmosphere, or other life-supporting conditions remains impossible for now. Nevertheless, given the structural and evolutionary similarities between Andromeda and our own galaxy, it's reasonable to assume that its planetary systems may be just as diverse. There may be gas giants orbiting far from their stars, rocky Earth-like planets in tight orbits, and frozen worlds lurking in the outer reaches. Some of these could resemble Earth, while others may be unlike anything we've yet imagined. An especially fascinating idea is that Andromeda could harbor planets shaped by its turbulent past. Unlike the relatively calm history of the Milky Way, Andromeda has undergone numerous mergers with smaller galaxies. These violent events could disrupt entire solar systems, flinging planets into new orbits or ejecting them into interstellar space. As a result, the galaxy may host a large population of rogue planets, free-floating worlds that wander the void without a parent star, especially in its distant halo. The environment of a planet in Andromeda would also depend heavily on its location within the galaxy. Near the core, intense radiation and gravitational forces likely make habitability highly unlikely. In contrast, the spiral arms could offer more stable conditions, similar to those found in our solar neighborhood. However, the presence of supernova remnants, dense star clusters, and even intermediate-mass black holes in various regions could create chaotic environments that hinder planetary formation or stability. Modern advances in artificial intelligence are beginning to aid in this complex search. Machine learning algorithms can now analyze vast amounts of astronomical data, detecting subtle patterns and anomalies that might signal the presence of distant planets. With continued progress, these tools may one day confirm the existence of planets in Andromeda, marking a monumental step in the exploration of the universe. To push the boundaries of space travel, scientists are turning to advanced propulsion concepts that go far beyond traditional rockets. Among the most promising is the light sail, a spacecraft driven by the momentum of powerful lasers. This concept is already being tested through the Breakthrough Starshot initiative, which aims to send tiny probes to Alpha Centauri by accelerating them with intense laser beams to a staggering 20% of the speed of light. Scaling this method for intergalactic missions, however, presents a massive energy challenge. Yet in principle, an enormous array of lasers could potentially drive a larger spacecraft to near light speed. Another bold idea involves antimatter propulsion. Antimatter is the most energy-dense material known, capable of releasing vast amounts of energy when it collides with ordinary matter. A spacecraft fueled by carefully controlled antimatter reactions could, in theory, reach extraordinary velocities far beyond the capabilities of chemical propulsion, though generating and storing antimatter in useful quantities remains a distant goal. If a spacecraft could travel close to the speed of light, relativistic time dilation would significantly reduce the subjective duration of the journey. Passengers heading for the Andromeda Galaxy might experience only a few decades on board, even though millions of years pass from Earth's perspective. Some researchers are even looking to cosmic phenomena like black holes and other extreme environments for possible solutions. Theoretical models such as the Alcubierre warp drive suggest that it might be possible to contract space in front of a ship and expand it behind, effectively allowing faster-than-light travel without violating Einstein's laws of relativity. While captivating, this idea remains highly speculative and would require exotic materials, like negative mass, which have never been observed. Another potential shortcut through the cosmos involves wormholes, hypothetical tunnels that could link distant parts of space and time. If they exist, wormholes might allow spacecraft to bypass vast intergalactic distances. However, no wormhole has ever been detected, and maintaining one would likely require unknown forms of exotic matter to stabilize it for safe passage. Some theorists argue that if intelligent alien civilizations exist, they may have already developed such advanced technologies. But even if we solve propulsion, the question of how to survive such a journey becomes paramount. Traveling across galaxies could take millennia or more. To sustain life on such a voyage, we would either need to develop long-term life support systems or find a way to suspend biological processes entirely. Inspired by animals that undergo deep hibernation, scientists are studying hibernation techniques for use in space. Another possibility is cryogenic freezing, though we have yet to master the ability to safely revive a frozen human. Alternatively, we may bypass human travel altogether by deploying self-replicating robotic explorers. This concept, introduced by mathematician John von Neumann, envisions autonomous machines equipped with AI and manufacturing systems that could mine local resources to create copies of themselves, spreading gradually across the cosmos and transmitting data back to Earth, without the burden of sustaining human life. Although such concepts remain theoretical for now, the rapid pace of technological progress makes them increasingly plausible. What once seemed like science fiction could eventually become reality. Yet propulsion is only part of the challenge. Venturing across the vast intergalactic void brings a host of engineering and physical hurdles. Speed alone isn't enough. Survival, precision, and endurance are equally critical. A spacecraft leaving the Milky Way to reach Andromeda would face severe environmental hazards, power limitations, potential malfunctions, and the sheer emptiness of space, a place where no resupply or repair is possible. One of the biggest threats is radiation. Within our solar system, Earth's magnetic field and the Sun's heliosphere offer some protection against cosmic rays. But outside this bubble, spacecraft are exposed to high-energy particles from exploding stars and black holes. Long-term exposure would pose serious health risks to humans, damaging DNA and increasing cancer rates, while also degrading sensitive electronics. To shield against this, spacecraft would need either extremely thick protective walls, which would dramatically increase their mass, or active shielding, such as generating artificial magnetic fields to deflect harmful radiation. Even if radiation protection was solved, travelers would still face the near-total emptiness of intergalactic space. Unlike within a solar system, where planets and asteroids provide occasional opportunities for landing or resource harvesting, the space between galaxies is almost entirely barren. Every essential supply, fuel, water, food, spare parts, would need to be carried from the beginning. Managing and preserving these resources over potentially millions of years poses a monumental logistical and engineering challenge. Conventional chemical rockets simply aren't up to the task due to their inefficiency. Even nuclear propulsion and ion drives, though more advanced, may still fall short over such extreme distances and durations. One speculative solution is the Bussard ramjet, a theoretical spacecraft that collects hydrogen from interstellar space using vast electromagnetic fields, then uses it as fuel for nuclear fusion. While the concept is unproven, it represents the kind of innovative thinking needed to tackle the problems of intergalactic travel. Another significant obstacle is navigation. Within our solar system, spacecraft rely on radio signals from Earth and the gravity wells of planets for guidance. But in the dark, largely featureless void between galaxies, traditional methods become ineffective. Stars fade into the background, and known reference points vanish. A spacecraft traveling to Andromeda would require an autonomous navigation system capable of recalibrating its position using whatever celestial signals remain detectable. One intriguing possibility is pulsar-based navigation, which would use the highly predictable signals emitted by spinning neutron stars as cosmic beacons. But even with perfect navigation, the spacecraft would need to endure incredible wear and tear over thousands, or millions, of years. As the spacecraft speeds through the vast emptiness between galaxies, even tiny hazards can become major threats. Microscopic particles like interstellar dust or micrometeoroids, though sparse, can erode a ship's exterior over time, especially at high velocities. To keep the vessel intact, future spacecraft may require self-repairing materials or robotic maintenance systems that can monitor and patch damage autonomously. For ships employing rotating habitats to simulate gravity, the moving mechanical parts would have to function without fail for generations. But the challenges don't stop there. Communication across such immense distances introduces another major obstacle. Even today, signals sent to Voyager 1 take over 22 hours to reach it. A spacecraft bound for Andromeda would experience delays not in hours or days, but in centuries, or even millennia. A message sent home might not be received until long after Earth's civilizations have changed or vanished entirely. This reality demands a new level of autonomy. Whether the crew is human or composed of artificial intelligence, they must be capable of surviving and operating completely independently of Earth. Traditional solar power, so effective within our solar system, becomes nearly useless between galaxies where starlight is too faint to provide meaningful energy. Fusion power, or other yet-to-be-invented sustainable systems, would be essential for a journey of this magnitude. If humans are on board, life support becomes a pressing concern. The ship must function as a closed ecosystem, endlessly recycling air, water, and nutrients. Even the International Space Station struggles with recycling systems that aren't 100% efficient. A vessel traveling for generations must get it right. Hydroponic or aeroponic farming could feed the crew, but ensuring long-term biological balance is a massive scientific hurdle. Then there's the psychological cost. Intergalactic travelers would live their entire lives knowing they would never return to Earth, nor likely see the destination themselves. Their descendants might be the ones to arrive, if at all. This raises deep questions about social organization, cultural continuity, and governance on a ship detached from the planet that launched it. One way to bypass the biological challenges is to send machines instead of people. Highly advanced AI systems, capable of independent thought, repair, and adaptation, could perform missions that would be too long or dangerous for humans. Still, even machines wear down. Components fail. Software can degrade. A possible solution: self-replicating machines, robots that can harvest raw materials, build new versions of themselves, and continue the mission indefinitely. As humanity dreams of reaching other galaxies, it's worth considering the fate of our own. Scientists already have a pretty good idea of what's coming. In the distant future, the Milky Way and the Andromeda Galaxy are on a collision course. Using powerful simulations informed by decades of astronomical data, researchers have been able to predict how this galactic encounter will unfold with remarkable clarity. Andromeda is closing in on us at about 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will begin their dramatic encounter. But this won't be a violent crash like two cars hitting head-on. Galaxies are mostly empty space, so their stars are unlikely to collide directly. Instead, gravitational forces will twist and stretch both galaxies, pulling stars and gas into long, luminous streams. As these tidal forces grow stronger, the once orderly spiral arms of each galaxy will begin to unravel. Enormous arcs of stars will be flung into space, creating visual chaos before the two galaxies gradually coalesce into one. Scientists have tested this scenario with countless simulations, adjusting mass, velocity, and galactic composition to model a range of outcomes. Most predictions agree. The Milky Way and Andromeda will undergo several close passes, each one more disruptive than the last. The initial encounter will be the most stunning. Andromeda's dense core is expected to slice through the Milky Way, dragging stars and gas behind it, triggering massive waves of star formation as clouds of gas collide and collapse. Some of these new stars may eventually give rise to black holes, further altering the gravitational landscape. With each successive pass, more of the galaxy's original structures will be stripped away. The spiral arms that once defined them will stretch and fade, forming immense tidal tails. Some stars will be thrown into deep space, destined to drift alone for eternity. Others will settle into new patterns as the merging galaxies begin to stabilize. Eventually, after several billion years of the celestial dance, a new structure will emerge, not a spiral, but a vast elliptical galaxy. This transformation is driven by the chaos of the merger itself, which scrambles the neat, disc-shaped orbits of stars. Instead of spinning in unison, stars will move randomly in a three-dimensional web, giving the new galaxy its oval shape. Elliptical galaxies behave differently from spirals. Without the ordered rotation of a disk, their stars mix more thoroughly. The legacy of the Milky Way and Andromeda will live on, not in form, but in the swirling population of stars bound together in a new, immense galactic home.